Okay, so this is a video talking about the different properties of the definite integrals. You should have your blank capture sheet with you, or your capture sheet that you use to fill in the properties using with the discussion or the Khan Academy page. So the first property is a sum and difference formula, or a sum and difference property. And what it says is if you have the integral from a to b of two functions added or subtracted, you can calculate those integrals separately and combine them to get your final answer. Because remember, a definite integral is an area. So instead of adding the functions together and finding a total area, it's saying I can find the area of f of x and then add or subtract that to the area of g of x, and then add those values and combine or subtract the values and get the answer to the integral. So I have two graphs here as an example with their integrals calculated underneath. And what the first one is saying is if we have f of x is x squared minus 3x plus 4, and if I find the integral from -1 to 4, that's this area here. And that calculates out to be 19.16 repeating. If I have another function, x plus 4, and I find the same a and b values that from -1 to 4, these, here's the property. These values of a and b, the start and stop values of your definite integral, have to be the same to the original sum or difference. You can't change your left and right bounds. So if I take, for my line, from -1 to 4, and I find this area, what I can say is then the integral from -1 to 4 of f of x plus g of x is the value of the f of x integral and add the value of the g of x integral. Works the same way. If I wanted to subtract, I could subtract them. Okay, the next property is the constant multiple property. And what the constant multiple property says is if I have a coefficient times a function, or if you think back to algebra 2, this was our vertical dilation value, we can either multiply the function and then take the integral and find the area, or I can find the area of just the function and then multiply by that coefficient or that constant. So graphically, this is what it would look like. Here's my x squared minus 3x plus 4 again. Here's my f of x. And then I graphed 3 times that f of x. I stretched it vertically by 3. So from -1 to 4, this area, again, was that 19.16 repeating. But if I stretch the function by 3, and I now do -1 to 4, let me get a different color. Now it's saying this area is 3 times the space as the original. So I could say 3 times the 19.16. So in integral notation, or down here, I have, this is our original function. That was what I colored in pencil, the small pieces, was 19.16. So if I multiply the function by 3 and find the integral, that area is 57.5. Or if I just take the integral first and then multiply by 3, the area, again, is 57.5. So typically, it's easier if I'm calculating, if I want to calculate the 3 f of x, I don't want to distribute this 3, graph a new function, calculate a new integral. I'd rather take the value I'm given, keep the 3 there, multiply, and get my answer. It's a more efficient process. Okay, the next property is the reverse integral. Oops, sorry. Center my paper here. Okay, so the way the reverse integral works is typically we start on the left and stop on the right with an A and B value. So again, if we go -1 to 4, we knew that this function gave us an area of 19.16 repeating. Well, if I switch my left and my right values, if I go now from 4 to -1 backwards, that's negative 19.16 repeating. So if I'm going backwards this way in my integral, it changes the sign, which is why we have this negative here. Because then this is the right value and the left value. If you think of the Riemann sums and these infinitely small rectangles between -1 and 4, instead of drawing them infinitely small, I'm going to just draw them with a base of 1. It's easier to see. Okay, so here's my left-hand sum. So if I go -1 to 0, that's a base of 1 times this height. Then the next base is 1 times this height, whatever that y value is. Then the next base is 1, here, times this height. And I'm going to get this positive area going from left to right. That's the original integral. Now if I go right to left, going backwards, this base value is -1 because it's a backwards length, or it's going from big to small. So it's a -1 times a height. So that's why this integral value has a negative coefficient. Okay, so the next property is the zero length integral. So it's saying start at A and stop at A. So I'm just going to pick the value of 1. So if I start at 1 and stop at 1, I don't have a rectangle. There's no base, there's no width, there's nothing here for my rectangle. So the value is 0 when you start and stop at the same left and right bound, because you have no area to take up. You haven't gone to the right or to the left at all. Okay, and the last property is the adding intervals. So what this property says is if I go from A to B of f of x and add then from B to C, instead of stopping at this common value, it's the same thing to go all the way from A to C to get the area. So again, here's our parabola we've been looking at as thinking of the areas for integrals. Definite integral means area. So -1 to 4 is 19.16 repeating. I got that value here again. So what I could do is I just said, okay, you know what? Instead of going straight from -1 to 4, let me go -1 to 2, and then again from 2 to 4. So I'm going to put a bound here at 2. So this area from -1 to 2, that integral calculates out to be 10.5. If I find the next integral from positive 2 to 4, this piece over here, from 2 to 4, that value, that area is 8.6 repeating. So by the adding intervals property, if I add these values together, I would expect to get the total integral of 19.16 repeating, and we will. So it's, if you're given two separate integrals, but they have an end and a start that match up, kind of like a transitive property. If A equals B and B equals C, then you can say A is C. So if these match up, you can just do one integral calculation starting at the very beginning and ending at the very end.